In this video, we'll be looking at answering the question of whether a given function is or is not differentiable. Recall that a function f of x is differentiable if and only if, that's what this expression here means, if and only if, meaning that this idea works in two directions, forwards and backwards, if and only if f of x is continuous and f prime of x is continuous. So this gives us a metric by which we can determine whether or not a function is differentiable. It's a two-part test. We first need to determine is the function itself continuous, and second, is its derivative continuous. Now recall that the definition of continuity states that as you approach a value, from the left and the right, you get the same value as you would at the value itself. In other words, continuity definition is the limit as x approaches a number of a function is going to equal the value at that function. And remember, if it's not written as a particular direction, this is implying both from the left as well as from the right. So both sides are equal to each other by default here, and the question is it also equal to the value of the function? So let's look at a couple examples. This first one states, determine whether the function is differentiable, continuous, both, or neither at the value where the function changes, where the rule for the function changes. So in this case, the only point of concern is at 5. It's asking us to think about what's happening at 5. So let's first determine, is f of x itself continuous or not at 5? Because if it's not, if f is not continuous, then we've already failed this first part because it has to be continuous, meaning the second part is not even relevant. So is f continuous at 5? Well, let's take the limit as we approach 5 from the left. So 5 from the left is below 5, meaning I'm going to be using this rule right here. So 17x minus 13. If I plug 5 in, I get 72. So from the left, I get 72. From the right of 5 means slightly more than 5, so from the right I'm going to use more than 5. So this top function, if I plug in 5 here, let's see what happens. 5 squared plus 35 plus 12. I also get 72. So from the left and the right I get 72. Incidentally, what is f of 5 itself? That means at exactly 5, or equal to 5, greater than or equal to 5. So I'm using the top rule again. So if I plug 5 into there, well, I just did that for the limit, direct substitution, I'm going to get 72. So is f of x continuous at 5? Yes, because all three of these are equal. So what remains is to find the derivative's continuity at 5. The question is the derivative continuous at that same point? So that requires taking the derivative. So let's go ahead and take the derivative of this piecewise function. Now that may seem like an exotic step, but it's not really that odd. The derivative of this function is also going to be a piecewise function, and guess what? It'll be the derivative of each piece. So x squared plus 7x plus 12, well, that would just be 2x plus 7. And 17x minus 13, well, it's a linear function, and its derivative or slope is 17. And each of these rules is valid in the same place as before. X is greater than or equal to 5, which I'm running off the screen here. And in this case, x is less than 5. So I need to now test to see, is this function f prime of x, is it continuous? So I'm going to approach 5 from the left into f prime of x, which means this orange guy. And f prime of x, 5 from the left is less than 5, so I'm going to be plugging that into the function 17. Well, there's nowhere to plug it in, really. I'm going to get 17 always, because this is a constant function. So from the left, my limit value is 17. From the right, meaning slightly more than 5, as I approach 5 from the right, I'm using greater than 5 values. So I'm going to plug it into 2x plus 17. So plug that in there, and I get 10 plus 7, which is, 10 plus, I should say 7. 2x plus 7. I get 10 plus 7, which is also 17. Promising. And what is f prime of 5? Meaning I'm plugging in exactly equal to 5. Well, that would use the top function again, greater than or equal to 5, and I get 17 once again. So all three are the same. So that tells me that f prime of x, the derivative of f, is itself continuous. So I get a check there. So we can say the following for our answer. F is both differentiable, F is both continuous and differentiable. I'm going to abbreviate here. At x equals 5. We get the same value and we get the same slope. Smooth transitions, a rate of change of 17 both before and afterward. Let's look at another example, another piecewise function. Now you'll notice algebraically, I kind of went through all the steps here to be precise, but really all we're doing is plugging in 5 into this, 5 into that, and seeing if we get the same thing. Then we take the derivative, plug 5 into that, 5 into that, see if we get the same thing. So I'm going to take kind of a more cavalier, less strict approach and see if I can get this problem done a little bit faster. So I'm going to plug 10 into my top function and my bottom function. So plugging 10 into the top function, I'll use a calculator here. 10 squared plus 8 times 10 plus 7, that gave me 187. And then plugging it into the bottom function, I believe I'm going to get the same thing. And since one of these functions is valid at exactly 10, I'm going to get the same number anyway, so yes, it is continuous. And you can double check that if you need to. I do, however, need to take the derivative carefully because I need to make this a new function, so derive and get f prime of x, and f prime of x will equal the derivative of each piece, which is 2x plus 8 in one instance and 18 in the other instance. And my handoff point is at greater than 10 and less than 10. Greater or equal to 10. So now checking my derivative values, if I plug in 10 into the top function, the slope more than 10 is going to be 2 times 10 plus 8, or 28. And if I plug it into the bottom function, well, there's nowhere to plug it in. I'm always going to get 18, and uh-oh. From the left, I get a slope of 18. From the right, I get a slope of 28. My slope suddenly changes from one value to another. This would graphically be represented as a change in the point, or a sharp change in the point, I should say. So this is going to be a non-differentiable point. So these are not equal, therefore f prime of x is not continuous. And if f prime of x is not continuous, therefore f is not differentiable. It is continuous, however, so we've established that, so the correct answer to this is it's just continuous. It's not continuous and differentiable like the previous one was, where both it and the derivative were both continuous. Here, just the original function is. We'll do one last example. It's a little bit harder. It states, given the piecewise function here, determine the answers at the bottom regarding continuity and differentiability. So this is actually guiding us as to something similar we did in the first problem. It's just that the problem's a little bit more nuanced. So the question here is at -1. So limit as x approaches -1 from the left. That might be hard to read, but that means from the left there. So that's going to be using this top function. From the right, so that means use the bottom function here based on the way the rules are written. And then at exactly 1, well, this is greater than or equal to, so I'm going to plug it in into here again. So these two are going to be equal by default because they're both using the same rule. So what remains is to find, are they all the same number or not? So I'm going to use a calculator here as well. 2 times -1 squared plus 4 times -1. So I'm plugging -1, I'll attempt to color code here a bit, into this top function, and I ended up getting -2. I'm going to plug -1 into the bottom function, so 4 ln of -1, interesting, minus 2, gave me also -2. And you can reason through that because the ln of 1 is 0, and that vanishes, and so on. Well, f of exactly -1 is going to use the same rule again, so that's also going to be -2. This tells me that f is continuous. All three were the same. The second part deals with the derivative, so I need to take that. When in doubt, just take the derivative, see what happens. So, oops, f prime of x. So this is a little more challenging. The derivative of the top piece is 4x plus 4, and that's valid when x is less than -1. The other piece requires a little more care, so let me be careful here. It says 4 ln of -x minus 2. So the derivative of that, well, the derivative, 4 is a coefficient, so just bring that. Derivative of ln is 1 over the argument times the derivative of the argument. So times the derivative of -x, which is -1. The derivative of -2, by the way, vanishes because it's a constant, so that's plus 0. So if I simplify this expression, the negatives here would cancel, so I'm going to be left with 4 over x. Again, plus 0 would also vanish. So this guy right here is just 4 over x. So not so bad, actually. So 4 over x. And that's valid when x is greater than or equal to -1. So plug a -1 into the pieces here and see what happens. So let's see. Probably don't need a calculator for this, but getting kind of sleepy. I get 0, and you can kind of see why, for that top guy. And then for the bottom guy, that's a hard color to see. Let's choose green. Plugging -1 into here, well, that's just going to be -4. From the left of -1, I get 0. From the right, I don't. Therefore, f prime of x is not continuous. I have a sudden change in the slope. My slope goes from 0, a 0 slope. Oops, let me color code this. I go from a 0 slope to suddenly a -2 slope, like so. So sharp point. So a function that has a continuous value for its function, but a discontinuous value for its derivative, this is actually just like the last problem, our function is not differentiable. Now there's two options that have not differentiable, but only one of them makes any sense at all. The two that have not differentiable are these two options, but did I say that right? Yeah. Well, sorry, let me backtrack. The only option here that we got to choose is a function is continuous, but its derivative is not, so our correct answer is this. Hope this helps.